Thank you for coming to the talk. I really would like everybody to bear with us a little bit because we're going to try and be ambitious and get the record for the most number of machines and probably the most number of demos that we've seen so far at NDC. I'm Nigel Parker. I am formerly the Chief Engineer for Microsoft Commercial Software Engineering across Asia, and I'm currently running a team of technical specialist engineers.
And my name is Dave Glover, and I'm a cloud developer advocate based here in Sydney. And yeah, all things cloud and IoT.
And I know there's been a lot of talks around IoT so far here at the conference. And what we want to do today is talk a little bit about the scenarios of using AI on the edge, disconnected from the internet, and different types of mobile endpoints. So with that, I'm going to get started. And I just want to kick things off with a little bit of a demo. So this is a little app I wrote on the plane, just to show some of the concepts that I'm going to talk about. The silence is deafening.
You got Wi-Fi?
I have. I told you there was going to be a lot of demos. No demo failure, though.
Hi Nigel, today you look 42 years old. Smiling makes you look older. I see a person wearing a Dracula mask.
Nice.
OK, you've got to give me a go.
No.
OK.
Let me try this. This is a photo I've got here. I'm going to try and actually just try and get it for the lighting.
Hi Nigel, that is a nice photograph of Indigo and Grandma. Indigo looks like she was 2 years old when this was taken.
Wow. What about here?
Hi Nigel, why are you holding that Dracula mask?
So Dave, do you want to
All right, I'll give it a go.
I see a 70-year-old male looking happy.
Now that's where you don't trust AI.
So I just wanted to start with a little bit of magic. Like any good magician, you can look at AI and you can think what's going on in front of you is kind of like the scenario that Dylan talked about at the start of the conference, which is the phone on the train, you press it, you get the message, and things happen. In this example, I'm using a lot of moving parts. And I just want to debunk and take apart some of the code that's come together to build this demo. So we've got a demo app called the Intelligent Kiosk that's out on GitHub. And it's also available through the App Store. And if it's going to load for me. Oh, it loaded just as I closed it. And what this is doing is, if I take a look at this image here, you'll notice that it takes a photograph of me, it goes away, it finds a lot of elements in my face, so the little dots around the eyes and the nose and the mouth. It goes away to the server. It then identifies that as a 50% match that it's actually me, because it's recognized my face, and it's thinking that I'm about 39 years old. Now, the age is a bit affected by the darkness and the lights that are up here at the moment.
Yeah, apparently.
If I try the Dracula mask. It's 82% sure that it saw Dracula in that picture. And if I try this example here with the photos with my daughter and my grandma, there it's identified Indigo, Grandma, and me at 37. Now, how's it doing that? Well, using the Face API, there's a little component where you can set up and train this model based on individual photos of people. So what I've done to train it is I've just given it only a handful of photos of me to go away and train from. For Dracula, it's actually a fewer number. It's just 3 photographs that it's seen. Grandma, there's a few photographs of Grandma in there when she's younger as well as when she's older. And the thing about Indigo, which is interesting, is there's no photographs of Indigo when she's a toddler. It's just photographs of her when she's a little older. And it's mapped that facial map, and it's taken it back, and it's identified her as a toddler or as a baby with some pretty good accuracy. So this in itself is quite an amazing process that we can go through. But this relies on a concept which I like to call, well, I don't like to call, it's actually called transfer learning, whereas a model has been trained using a significant number of data points, and then that model is being used to retrain and solve a new problem using a few extra data points attached along the way. So I know there's been a lot of sessions so far at NDC that have been talked about neural networks and primers to AI, but I just wanted to cover a couple of things here so we can set the scene for the rest of the talk. There is many types of common deep neural networks that are used inside of AI, and I'm going to spend a little bit of time on computer vision talking about deep convolutional neural nets. There's also recurrent neural networks that we use for language processing, deep belief networks for speech and music, and deep reinforcement learning is often used in gaming and retail type scenarios where you're looking for fraud or you're looking for buying patterns. And in computer vision, there's really only 4 types of tasks. And these go back sort of 20, 25 years. The first one, image classification. This is the hot dog, not hot dog example from Silicon Valley, where it's looking at the whole image and it's identifying that image against pretty much a single tag to determine what's in the image. Object detection, that's another form of image classification where it goes across the image and it looks within the image to try and match multiple things within the same image and then find out where within the image it is. And the reason it uses a square box around it is it's this idea of a sliding grid that goes across and then it can be identified. So if you think about a process where you're doing object detection, you're actually doing, in most cases, there are some exceptions, lots of image classification steps across a larger image to determine those bounding boxes. The more advanced side, image segmentation, that's exactly where in the image it is. So that's really cutting out the pixels. So if you think about advances in autonomous driving, those kind of processes are really around image segmentation, which is the future. And then image similarity is when I see this, what is a similar version of this? So identifying a class of objects and then looking for other versions of that class using things like image search. And the concept of deep learning, so traditional machine learning, you generally have a data scientist who understands the data points in the problem domain, and they apply their knowledge to extract the features that are important within the data set. With deep learning, a lot of that feature extraction and classification happens automatically within the algorithm, and the algorithm itself can determine the steps along the way. And that's called the convolutional layers in the network. And then the connected layers at the end put that all back together to answer the question that you're looking to solve. So is this a dog? Is this a cat? Is this a car? And when you think about the neural network that is just coming back to solve that problem, what you can actually do, and I talked about, this is kind of how it works. So at the start, you get the low-level features out. So you get things like gradients and colors and angles. It then goes into higher-level features, so things like corners, contours, simple shapes within the network. And then more complex shapes, things like wheels and faces and images, and door frames. And then the fully connected layer will put back together the complex scene. So it will take all of those components and it will reconstruct that to solve the actual problem you're trying to solve. And I talked a little bit before about transfer learning. A lot of solutions that you use, like if you're using custom vision AI or Google's image service, they're really using transfer learning behind the scenes. So the algorithms have been trained off millions and millions of photographs, and then what they're doing is they're actually extracting those final layers and they're attaching a new set of layers to answer a new problem. So if I wanted to take that pre-built example for the cat, dog, and car and ask, is that a deer? It's then going to strip that output layer off and then recreate a new output layer, which is going to answer that particular question of, is this a deer? So that's kind of at a high level the concept of transfer learning that we see a lot when we start to work inside of this kind of space. And anyone know what this is? Any hands? There's a couple of hands. So ImageNet, the reason this is possible now, like we hear about the buzzwords around AI, but we've been doing this for a hell of a long time. But there's a few things that have happened that's made it a lot easier today. One is there's a massive amount of digital data available, and a lot of it is now tagged and identified against what the physical objects are. This is digital audio, it's photos, it's a whole bunch of data. The other thing is the algorithms themselves. So we're getting smarter in the algorithms that we're using to determine and solve the problems. And then the third one is the compute power required to do a lot of this. So to do the more advanced versions, there's a huge amount of compute that's needed to go away and perform those problems. So in 2012, ImageNet kind of came around and decided that they were going to do a global competition called the ILSVRC, or ImageNet Large Scale Visual Recognition Challenge. And that was really around challenging people to get the best results from their image set, labeled image set of like 10 million photographs. And there was a guy called Alex who created, humbly, AlexNet, and he won that competition in 2012 with a deep neural net, which had, I think, 4 or 7 layers, 4 or 5, 8 layers, there we go. And then 2 years later, VGG won with 19 layers. And then GoogleNet came along and introduced a 22-layer neural net, which also took out the competition. And this was a little different because it had this concept of inception, where it looked back in on itself, and then it repopulated as it went through the network. Then in 2015, Microsoft came along and won the competition with an algorithm called ResNet. Now, at the time, nobody thought a neural net could get this deep, but they proved by creating a 152-layer neural net that just kept going and going and going, that it wasn't actually going to overfit. And there was a huge amount of data within the visual images themselves that could be refined by a neural net to get better results than we'd ever seen before. Now, at that point, this competition was kind of almost done, because moving on from 2015, people were winning with what we call ensembles. They were taking Google Inception and adding Microsoft ResNet, putting them together, and then training them in iterations and basically taking out the competition. So then we sort of moved on to this next model, which was COCO, which is Common Objects and Context. And this was the ground around segmentation, and this was the place where we were looking beyond the classification of a single image and started looking within the image to find components and pixels. And this is the base point of where a lot of the autonomous driving and detailed image recognition technologies are coming today. Now, out of this data set, this was won by Google, who used Inception v3 and ResNet together to perform the outcomes of the first competition on top of COCO. Democratizing AI. So you may have seen an announcement last week that Microsoft was acquiring this startup called Lobe. Anyone seen that? So Lobe.ai, they're a new startup that has come about really in the last 6 to 12 months, or they've become public in the last 6 to 12 months. And what they're really doing is trying to take a lot of this computer vision stuff and making it drag and drop and readily available for people who want to build different scenarios for solving problems using these kind of techniques. So I'll just play this little video here to show you an example of how this is working inside of the Lobe application.
Water into this big storage tank, and on the outside of the tank there's this crude gauge made up of a PVC pipe attached to a string and a pulley and a float inside of this tank. So basically, when the water level in the tank goes down, the pipe on the outside goes up. To help keep track of our water usage, I set up a Nest cam pointed at the tank and taught Lobe to find the different elements in the gauge and then tell us how many gallons of water we have left in the tank. So you can see down here a bunch of different examples I collected of the gauge in different lighting, day and night, at different levels. So then over here in the image, it's been able to figure out where those different elements of the gauge are and then calculate how many gallons of water we have left in the tank. And so once a model's been trained in Lobe, it can be easily integrated into an app by either downloading a CoreML or TensorFlow file. These can run directly in an app on device without any internet connection. Or you can integrate your model using Lobe's developer API. Code snippets are available in several different languages. So for example, if we were developing a web app, we could select JavaScript, then copy and paste the code into our app. It will send Lobe an image, run it through your model, and then send you back a result all over the air. So using the Lobe API along with the NestCam API, I was able to create this website where I can go and see a live feed of how much water we have in the tank. I even have this graph down here at the bottom of our water usage over the last week. And so this has been really useful for us.
So this is really using the technology to take what was an analog solution and monitor it using vision and then publish it out. And there was a key point in this video where he said you can export that model using Core ML or TensorFlow. So part of the challenge right now is how do we export the models to reduce, so when we export the model, we have to really shrink them to make them work disconnected. And there's not really a standard for that. Well, there wasn't a standard for that. So Apple created Core ML, which sits inside of their iPhones, which is a way of actually processing and running some of these models offline. Google then took their TensorFlow process that they use at scale and then started introducing that as TensorFlow Lite or TensorFlow Mobile. I don't know why I want that. And so by doing that, there was a lot of different formats that you had to actually support and start to develop for. So we got together with Facebook and Amazon and some others, and we started creating this concept called the Open Neural Network Exchange, which is ONNX. And ONNX.ai is intentionally designed to enable models to be exported and used universally across different types of hardware and devices disconnected from the internet. So I'll get onto that a little bit more. And then we talk about why the edge. Well, you don't always have access to an internet connection. You don't always have the ability to go back to the cloud to get the answers that you want. So that demo that I showed at the beginning, that was connected to Azure and then using our cognitive services to match the Face API to go back to the cloud to get the answer, to come back, and then to run locally to speak the response. Now, that demo wouldn't work at all in a scenario where I didn't have an internet connection. But there are other scenarios, and there's plenty out there where you would want to have those type of things work locally on a device. So if I just bring up here, sorry, I just disconnected. Damn it. How did that end up being connected? Sorry. There you go. So I want to show you a couple of things here. In New Zealand, Te Reo, the native language, is a language that's being forgotten over time because the last generation of Indigenous people didn't learn to speak it, so they're only speaking English. So there's been a process in New Zealand around rebirthing the language. And so our largest telco got together with Google and created an application called Kupu that came out last week, which is really designed to help take photos of common objects. So let's see, Dave, are you a common object?
I'm a common object, apparently.
And this goes back to the cloud. It identifies what's the image, inside the image. It finds all the feature points, and then it provides you the translation in Te Reo that you can speak back and understand that definition of that word. So there, glasses, mohiri, and it can speak that down. And down here, you'll also see eyewear and products and other definitions that can be described. So this is a really good scenario for maybe learning a new language or identifying objects and finding new things. Now, the challenge with this is it's really complex in its model, and it would really never work offline. We have another application, which is Seeing AI. Now, Seeing AI is designed as an aid for blind people so that they can actually work disconnected from the internet. So you see here, if I point this down, at this
registration. Welcome to NDC Sydney 2018. On behalf of the entire NDC team, thank you for taking out of travel to Sydney and be a part of NDC Sydney 2018. Venue. Both the workshops and the conference will be held at Hilton Sydney. Person. 2 faces. 0 faces. Nigel near centre 2 feet away. 2 faces. 1 face near left edge 3 feet away. 1 face near centre 2 feet. 2 faces.
And so that itself is disconnected. That's not running connected to the internet. That's working in real time, 0 latency. And that's been created by a blind engineer that we've got at Microsoft along with a team of accessibility people and released on the App Store. Now, the only reason it's only on iPhone is because it relies heavily on core ML, and we haven't been able to get the same capability out of TensorFlow Lite yet to actually release this on another platform. But it's a good demonstration of maybe the different scenarios and where you'd want to play together with these two things. So with that, I'll hand over to Dave to talk a little bit about IoT Edge and the primer for disconnected devices.
Look at that, it works. So far. Alrighty, so this segment here, we're going to talk about what we're doing around extending Internet of Things scenarios and extending that kind of intelligence on the cloud, or in the cloud, kind of down to our devices. And the analogy, I've got a bit of an analogy, and I want us to all step back to when we're at school. And in this case, I'm not stepping back to those maths classes, which I suspect a lot of us are all thinking, wish we'd kind of concentrated on a bit more. But we're actually going to step back into our biology classes. And if you remember, we almost invariably studied our nervous system. And we studied the central nervous system, which was basically our brain and our spine, and we kind of like central processing kind of going on. And the other thing we had was our peripheral nervous system. And the peripheral nervous system is responsible for picking up, touch, sense, smell, things like that, and then be able to control our muscles. And we can kind of make all of that work. And there's two nervous systems which are kind of working together. Now, most of us appreciate that if we go and touch something that's really hot, we kind of get what's called a reflex arc. And what's actually happening in that scenario there is instead of that message going from our fingers all the way up to our brains, and the brain's saying, oh, I think you touched something hot, might be an idea to move your hand away, which can take hundreds of milliseconds, we have a reflex arc, which goes, basically the message goes to our spine, and our spine then short circuits that message and tells a twitch of a muscle and pulls back a hand. And that's kind of more in the tens of milliseconds. And that's obviously a really nice design in terms of trying to protect ourselves. So that's one thing that's kind of really important about how our bodies work. And it's the ability of our short circuit and do things really quickly with a low latency. The other thing that we've kind of evolved, or have you look at it, is our vision. So about 30% of our cortex and our brains is around vision processing. And our eyes are actually an extension of our brain in many respects. They are, in fact, an extension of our brain. And there is a high-speed connection going into our visual cortex, and that's the thing that's doing the processing. And then it's sending messages across to other parts of our brain to say, hey, look, you might want to think about this, or take this action, respond, or delete, or save into memory, or analyze, or whatever. You can think of those kind of scenarios. So those are kind of two things that kind of work. So we've kind of got this peripheral system, we've got our central nervous system, and we've got these reflex, and we've also got our eyes, which got a high-speed connection. And that's very much the analogy about what we're doing when we're thinking about our Internet of Things. So today we have the Internet, so Azure IoT Hub, and for most scenarios, you've got a device sitting on there, and day to day, they're just sending out telemetry, and life's good. And that will cater for most things. And you can, IoT Hub is there for mass ingestion of data, about tens of millions of devices you might have out there, and be able to respond back to those devices and say, hey, look, you might want to turn that valve off or things like that. Now, there are a whole set of other scenarios where sending a message up to the cloud and saying, hey, look, this lathe has suddenly started vibrating, and you're going up to the cloud and doing some sort of logic up there, and sending a message back down, and maybe that's a couple of hundred or a couple of thousand milliseconds by the time you get that message down, and by that stage, it might be too late. So what we're trying to do is kind of emulate this kind of peripheral, the reflex arc, and those types of ideas. And where you've got a lathe, let's say you've got Internet of Things, you've got IoT Edge sitting on there, which is monitoring a lathe, which is spinning at X number of thousand revs per minute, and a ball bearing busts. And in this case, the message will go straight to the IoT Edge device, which has intelligence on it, and then that can send a message to the lathe and say, hey, look, I think you should stop. And then at the same time, it could also send a message up in its own time fashion up to the IoT Hub in the cloud and say, hey, look, there's been an alert. You should do something about it. You should get someone to look at this, maybe replace a ball bearing or whatever it might be. So that's kind of the idea behind that. So that was kind of more this reflex arc idea. The other thing is that a really common scenario, and particularly for security cameras, that they're dealing with huge quantities of data. And realistically, it's unrealistic to go and ship all that data up into the cloud and process it all up there. So what people are doing, what organizations are doing and building are these smart cameras or the IoT Edge-like devices which have algorithms running in them, and they are processing, and they say, hey, look, there's a person there. I've seen that person in that shop, and then I've seen them in that shop, and they've left a bag over there, and they've done blah, blah, blah. And they can kind of follow and start pulling together scenarios of what people are doing, and then just sending out more the metadata and maybe the interesting frames up into the internet for additional processing. So that's the kind of idea. So very analogous to this kind of how our nervous system works overall. And that's what we're doing with IoT Edge, to provide this highly responsive, low latency, dealing with lots of volumes of data. But also one other area which we're looking at, which we cater for, is a lot of organizations, particularly industrial process control systems, they'll have SCADA systems or OLE process control systems, which weren't really built for internet protocols. They're not secure protocols. So those are things to be able to bridge those protocols across via IoT Edge and then out onto into the internet. So kind of give you a few of the design principles. One of the most critical ones is obviously security. So one of the things we do with IoT Hub in general with devices, that each device has an identity, has a certificate, and you can pretty much guarantee that that message has come from that device and has gone up into the system, or else you get the device won't be able to transmit. And that's the same philosophy that we have with IoT Edge with the appropriate hardware. So you have to have a piece of hardware out there which has effectively a TPM, so a trusted platform module in it. And what we do with IoT Edge is that we trust all the way from the device drivers to booting up the system to starting up IoT Edge, to starting up the runtime for IoT Edge and loading up various modules. So that's really a critical part of it. But as I said, that does require dedicated hardware support. And you tend to go and buy these devices from people like Advantech or Bosch or people like that who are doing industrial level process control systems and sitting out there. The other part of it is, of course, as soon as you start getting logic out onto the edge, you start getting to this, heck, how the heck am I going to start managing this? And then one of the things we do with IoT Edge from the cloud is the ability to define what modules are going to be running and executing on the device. So you basically set up some metadata. That metadata gets pushed down to the IoT Edge device that says, I need version 2 of this module. It then goes up to the cloud and pulls down the module and restarts itself and then starts a new version. So obviously super critically important to managing potentially a lot of devices out there and making sure that you know what version of software they're running or being able to update their software. The other thing that a lot of people want is store and forward and being able to support partially, and I do say partially disconnected scenarios where you might have a factory which is sitting out somewhere in the back of beyond and there is limited connectivity. At the moment, you do still need connectivity to initially basically bootstrap and get the security and get authenticated against the cloud. But once you can, if you lose your network, the messages can be stored, and then when the connection comes back, they can be forwarded back up again as well. The other thing that we support out there is both Linux and Windows. The reality is, for these industrial type devices, which will be typically running these edge devices, most of them are running a version of Linux. It's a hardened version of Linux. There are Windows devices out there, but the majority of these devices that we're talking about, these edge devices, are probably going to be running on Linux. So it's really fascinating to see that we treat both Windows and Linux as first-class citizens with the IoT Edge. In fact, I'd argue that we actually treat IoT Edge on Linux a bit better because actually that's released first than it has on Windows. And also, it's all open source. It's all up on GitHub. You can go and check it out. You can go and clone it. You can play with it, add to the documentation, things like that. So those have come to some of the design principles behind it. In terms of actually building this stuff, you build it with Visual Studio Code, so the tools are all free. You can go and build it on Mac, Windows, and Linux. I personally tend to build this stuff on Linux, mostly because I want access to the camera, and you do all this inside Docker, and you need the camera to be able to break through and effectively into the Docker container. When we have SDKs for pretty much every language, I actually think I'm actually missing C off that, so we actually have a C SDK up there as well. And you can target devices which are x64, ARM-based devices, and Windows on x64 as well. Now, part of my demo, I've actually got a Raspberry Pi up here. And I should kind of caution that when we talk about ARM and Raspberry Pis, I do see this occasionally. is that Raspberry Pis, as they stand kind of off of retail, they're kind of prototyping devices. If you want to go and do something in anger, you would typically take that Raspberry Pi reference architecture, you'd go off to someone, the name escapes me now, and you'd say, look, I want these in production qualities, and I want a proper disk on them, and I want a proper bit of X amount of memory on them, and things like that, and these devices, and these drivers, and blah, blah, blah. So that's typically what you do with those types of things. And the other thing that you need is Docker, because this system is heavily built around Docker. So you need access to a registry. And that could be either the Azure container registry or Docker Hub. And when you're building these things, my really strong recommendation is that you set up a local Docker registry on your development machine. And you can see there's Docker run, and you typically put this on 5,000, port 5,000, and you run Docker registry on your own machine. The reason behind that is when you're developing and testing and debugging, of course, you're coding up, and then you've got to push it up into a Docker registry for then to end up on the device to test it. And of course, it's going to break the first time anyway, for me, multiple times. And that can be a really slow and laborious process. So the idea behind it is you build as much as you can on your development machine, and you push it to a local instance of Docker, and then it gets deployed onto the Docker environment, into the IoT Edge environment, and then you can hook up debuggers, and you can step through it and figure out what's going right and wrong. So that is my biggest lesson I learned with this stuff, is deploy out Docker locally. In terms of, we had this thing called the runtime, the IoT Edge runtime, and it fundamentally has three concepts. It has the idea of a module, and a module is just really a Docker container. And obviously, you go and compile them up, put them up in a Docker registry, and then you go and define them. You have something called a device twin, and a device twin is the idea of being able to send data down to a device and have a device report up. So you talk about what's called reported state and desired state, and there's the typical technology or terms that you use for device twins. And you basically set up metadata which describes what modules. I want this version of this module. I want this version of module, these two versions of the modules. And then you go and define things called routes. And routes are basically how modules are going to talk to each other. So just basically, there's a messaging substrate, and you just go and describe this module is going to be outputting on this known name, and I've got another module over here which is going to listen on this name, and it's going to be picking up information off that and doing some sort of processing. So that's the kind of idea and how this stuff works. So basically, three concepts: modules, which are really just Docker, and device twins. And when you go and build this stuff, as I said, you go and develop your containers. You use Visual Studio Code. There's a couple of extensions that you want to make sure you got there. You push the stuff up into containers. You go and provision your device, which is basically, effectively, you need to get the connection string for that device from IoT Hub onto the device. You need to go and set up your definitions of your modules. You need to go set up your routes, and you need to go and define any parameters, any runtime parameters you might have, environment variables would be kind of a common way of doing it. And that's pretty much it to actually go and get things out. So what I've got here is a bit of a demo, and I'm going to run you through some of the things you can do around IoT Hub, just kind of give you a bit of a sense of that. We've got a very quick custom vision demo, which I think a lot of you probably already seen custom vision demos pretty much every day. And the other thing I'm using is Bing Speech. And I'm going to nick this, and I'm going to plug this in, and it's almost certainly going to buzz the speakers. So just bear with it. Ah, it didn't. That may mean it's not turned on. All righty. OK, so the first thing I'm going to do is go across to Azure. And this is the IoT Blade. And you'll see down there, if you've played around with this or you haven't looked at this recently, you'll see there's a new blade in there called IoT Edge. And in here, you'll see that I've got a number of devices which are set up. And if I make this a little bit bigger, you'll see I've got about 7 or 8 devices set up there. And these are all running code and executing. And so what I've got here next to me is this Raspberry Pi module, which happens to be the one on my desktop. And if I scroll down there, you've got information like connection strings and yada, things like that. And then you start seeing what modules are actually executing on the Raspberry Pi in the context of the IoT Edge runtime. And you'll see that what I've got on here is I've got a camera. And so I've got one module which is responsible for running an OpenCV camera module. So it's basically going in a loop and basically taking photos. And then I've got another module over there which is called an image classifier module. And I'll tell you how I built that in a moment. And basically, the camera capture module is calling over a REST point into the classification module and passing across the image, and it's scaling that, scoring that image, doing a prediction on it, classification on it. And if I go into camera capture, you'll start seeing, if you remember before I talked about device twins and this idea of desired value and reported value, and that's what this is. So you can see that the system over here is reporting that I'm running an ARM container, which is great because it's Raspberry Pi, and what version of that image. And then you can see I'm pointing off to Glovebox, which is my Docker Hub ID. And then you can see the version, all those kind of the last reported dates and things like that. So this is basically a device twin in action where you start seeing this data. We've also got these things called create options. Now, appreciate that you can't actually see that clearly. And so what these are is that this is basically telling Docker how you need to behave. And in this case here, I'm telling Docker that I need to break through to the video and get access to the video stream, although in this case it's called, on Linux, it's dev/video0, and I'm representing that back inside the container as dev/video0. And the same thing with dev/sound, because I want to get access to the sound card. So I'm basically, all the things that you know about Docker, you do -p and the port and things like that. This is where you put the equivalent of that. And you put it into this JSON document, and it ends up being shipped down to the IoT Edge runtime, which calls upon the Docker API and presents these parameters and says, OK, I need to set up video, and I need to set up sound, and I need to instantiate this container and get it up and running. So that's what's going on there. And if I come back to the twins, and then I'm just going to go into set modules. Now, what you can do is that there are obviously modules that you can go and build yourself, which is probably the very common scenario. But plus, you can go and add in both first-party modules, so in which case Microsoft do a number of modules. We do a stream analytics module. So you can go up into Azure and go and build your stream analytics. I don't know if anyone's done this. And it's real-time data aggregation. And in this case here, what I've done is I've enabled the stream analytics job for IoT Edge. So you'll see there's an option down there. So just jump back across over here. And you can see that there goes that temperature alert stream analytics job. So I can go into the portal, create my stream analytics job, and I can actually export that job down to IoT Edge and have that actually running, sitting down there. So you can hope you get the general sense. You go and create your devices. In fact, there was one other thing I wanted to go and show. Jump back over here. So we have individual devices, but we also have edge deployments. And actually, sorry, I don't have anything set up in this one. But this is the idea that you probably want to go and treat your edge devices in groups. I know it's the South Australian-based retail outlet, for example, and I want to go and update all those. It's Christmas Day, and that seems like the perfect day to go and update all the devices. Mm-hmm. And you can kind of do things like that, and obviously make more sensible decisions than that. So the next part I want to show is custom vision, and I think probably most of you have already seen custom vision. So what I've got here is a whole lot of training data, and most of this data I actually got from a data set called Fruit 365. And there are 50,000 images of fruit that people use to train. So if you do want some data sets and things like that, this is a great data set to work with. It has one really big disadvantage. Does anyone know what the disadvantage is? Put your hand up. OK, it's really uniform. It's almost a bit too uniform for real life use case. It's great when you pick up a kind of like a nice image and you just pass it across of an apple, and yes, it'll do that. So what I've done here is I have tended to mix it up a bit with images, sitting in a fruit stall and things like that. And so you need to get your data. You need to make sure it's kind of all looking right. But variety is definitely the spice of life when it comes to these images. And then the other thing you need to make sure you're doing is that when you're going to export this model, which I'm about to do, is a TensorFlow Lite model, you need to make sure it's a general compact, in this case, or landmarks or retail, but the compact versions. And then when you've done that, you'll notice that there is an export button up there. And this will enable you to come out there, and you can see there's multiple places you can export it, and you can go and select the platform. In this case, you can select out Linux or Windows. And if I come across to this solution over here, open it up, what it would download, this is the model that it downloaded for me. It downloads all the infrastructure. So it downloads my Docker. It downloads my model. You can see I've got avocados, bananas, Granny Smiths. It downloads the TensorFlow Lite model. It downloads the mod you're going to call for predict, and also for an app. And this basically generates a Flask-based Python application for you, which is going to listen on that point called image. And that's kind of how that works.
And that TensorFlow Lite model there, that's about 5 megabytes, is it?
No, I think it's actually about, for that model, it's only about a 1.8, about 2 meg.
2 meg.
So it's pretty small. And actually, it executes pretty damn well on a Raspberry Pi. So as I said before, so this is a great starting point. You get your Docker image, you got your model, you've trained it up in the cloud, you pulled it all down, and then what you're going to do is you're going to start building an IoT Edge application. And then what I'm going to do is jump around over here. And I've got a couple of extensions. One's called IoT Edge. And if I go IoT Edge new, I can go and build a new solution. Select the folder, take with the default name, and then I get the option to go and build modules. So yeah, I've taken that Docker image before that I've created and things like that. And I can come down here. In this case, I'm just going to stick with Python. And I can go and build my sample module. By default, it will set up your Docker as pointing at your own local registry sitting on localhost 5000. Goes and creates that, uses this module called Cookie Cutter, and that creates you this module. And you can see through here, I've got my Python, standard bit of Python that's got to get you started. And it's created you the Docker images for building for both ARM32 and for debug on ARM, AMD 64, et cetera. And any requirements, any Python pip requirements that you might want. And then you can come along here, and I can say, in this case here, I can go and do and build. And you'll see up here where my mouse is, I can go and build for AMD 64, ARM32, et cetera. And then it'll go off and build that. I'm not going to do that right now because we've kind of been there. And then really the solution which I'm going to show is this solution. So pretty much went through the same process. I went up to custom vision. I exported that Docker module. I then pulled it down to my project. I created my other module, which I actually really did create, which was an OpenCV module. The reason I went down OpenCV is it works both on my desktop and on my Raspberry Pi. If I went down the Raspberry Pi and just used the Pi camera, things like that, then it just kind of gets a bit awkward when you want to test on the desktop. And so these are the two modules. And then down here, you effectively have some metadata. And this metadata basically is the data that's going to go up into IoT Hub and describe the solution to IoT Hub, which is then going to take that metadata and push it down to the device. And that device is going to say, I want that particular module on AMD, for example. And in fact, I've jumped around slightly, but it doesn't matter. It's basically describing the modules, the relationships between those. And then somewhere in here, it's telling me the routes or the routes that these messages are going to take. So this module is going to talk to this module, and this module is going to send a message up to the cloud. And then lastly, I've got the last thing I've got in here. So and then I can go and deploy this. And so basically, you can go and build and push this. And if I did this, it's going to run against just the local Docker registry. So it's going to be super quick. And then when I've done that, I've got this deployment up here, and I can go and say, create for a single device, and hopefully it'll bring up all the devices that you spotted in IoT Hub, which are IoT Edge devices, and then I can go and deploy it. I'm not going to deploy it now because it's going to be over my phone and life's too short. And one of the things that you might spot on the kind of main Explorer panel is when you've got the IoT tool set in there, you can come along. In this case here, I've got the Raspberry Pi, and I'm going to monitor device-to-cloud messages. And with all things being equal, and what I have to say is I can't hear the sound.
You scanned an orange.
OK. So now,
you scanned an avocado.
so what's going on here? Now, it thinks, unfortunately, the model thinks that this desktop here, the
You
black,
scanned an orange.
is most likely an avocado.
You scanned a banana. You scanned a red apple.
Yeah. Now, the funny thing about it is that why does it keep coming up with bananas all the time? And what I figured out is the shape of my hand. And so when I'm putting the apple under there, it's picking up my hand as a banana.
There's a
apparently.
good lesson here, because when you're building classifiers like this, if you don't have negative
scanned an
examples,
orange.
It tries to match everything it sees as one of the things in the example.
Yeah. So what I've done to try and get around the fact that I haven't put any object detection in here is I've got the camera really close just to kind of cut out the clutter. And if I got another one over here,
You scanned a Granny Smith.
well, hey, that works. So that's the kind of idea. So you get so what's happening here? The Raspberry Pi is running that model that I've exported out from Custom Vision, and I've got the OpenCV camera support going around the loop, sending messages, the images off to that model, and then I'm calling the Bing Speech API, grabbing pushing the label up into Bing Speech, and then pulling that back down and playing that through the speaker. So that's basically how. So I could chuck in nothing out. And as you can tell, the Bing Speech APIs actually does a pretty damn good rendition. And I just cache it because it's all the same. I've got limited objects. Now, as I'm coming through here, you'll notice that I'm also getting these messages up on my screen. And these are the messages which are going up to Azure.
You scanned a banana.
And you can see...
You scanned a Granny Smith.
whatever. But you can now start seeing, remember I talked about that reflex arc and having
scanned an
local
orange.
intelligence? We can we'll unplug it now because it's going to get irritating. That was. But you kind of get the idea is that you can see the messages, and in this case, I'm just sending out the metadata up into IoT Hub and then doing something smart with that metadata. So hopefully it kind of gives you a bit of a sense of what's going on. Back over to you.
Thanks, Dave. So with that scenario, that was really demonstrating using IoT Edge to go down onto a client device that's running Linux. I did talk a little earlier around this concept of ONNX, which is the Open Neural Net Exchange. With Windows, the next version of Windows, or the insider builds that we have at the moment, we're moving to support the Open Neural Network Exchange inside of Windows natively. So it takes advantage of the GPU in your machine. You can program against it using .NET or C# or whatever language you're most comfortable within. And with this, there's also this Azure AI gallery. And I know Azadeh showed this earlier in her talk, how to take an offline version of a model which could test face and work out behaviors, and build a C# WP app that could actually do that. Inside here, there's actually an example of YOLO, which stands for You Only Look Once. Now, YOLO is an object detection algorithm that works a little differently. It doesn't go gap to gap. It actually looks at the image one time and then works out through grids, identifying bounding boxes. So if I wanted to create a version that could take the YOLO ONNX model, I can do that by downloading it from the gallery, which is the gallery.azure.ai. I could create a new WP app using a camera control, and then I could drag, as long as I've got the tools installed, the SDK installed, I can just drag the model itself into the project over here, and it will create a nice little helper file for me that will actually look inside of that model, work out what the input should be, the input sizes, and it will do auto-scaling and auto-changing of my images that come in to match that output. And then I can take the output from the model, and then I just need to program a helper class that can identify it. So here's a helper class for YOLO. YOLO's trained on VCNet 20, so it's got 20 labels that it's going to identify, and it will look at the output from that model, and it will identify which of those labels is actually there inside of it. So if I was to run this example, it's going to load up the UWP app on my machine, and I'll give it access to the camera. And here it is here. So it's now in real time processing and looking, seeing, what's it see? See another person, see a couple of bottles there. And it's doing this completely offline using that YOLO model. If I was to turn the camera around, what's it going to see? It sees a big sofa. That was chairs earlier. And it just so happens that there's a video on YouTube which is 36, what is it? Half an hour of cars driving down a street, which is really useful for demos like this, where I can just hold that in front of it and it can start to see cars and people and dogs.
Does it detect the number plates?
It's not trained for number plate detection, it's just trained for those 20 classes.
Yeah, of course.
But what's really interesting is you can start to see how this could work on mobile devices and how it could be used inside a disconnected scenario to do real-time object detection as a first pass before it sends an image up to the server. So you want to make sure you don't send the photos up until you see a certain thing in them, and then once you see something, you can send it up with these kind of bounding boxes. So that's the YOLO demo. I also built a classifier in Custom Vision, and I've got a blog post that I share in the links at the end on how I did this. And what I was doing was I was training based on a bunch of native birds, because it's quite a common scenario to go to a new country and not necessarily know what type of bird something was. So you might want to identify it from its photo or from its bird song, and then determine from that, what is the actual bird that you're looking at. So I used images from the Bing Image Search API and trained based on a bunch of New Zealand native birds. And in this example, this is an object detection one as opposed to a image classification. So depending on what threshold you want, like you say, I want it to be 60%, only identify 80% accuracy, and I'm okay with the bounding boxes overlapping kind of 38%, and then it tells you what your recall is and what your precision is based on that. I've got a blog post that talks about how to structure these images and doing image pre-processing and avoiding overfitting and looking for real-world scenarios that I link to as well. But with this demo, coming back to the intelligent kiosk, there's a Custom Vision Explorer. And because I've connected my keys to my version of the Custom Vision, you'll see I've got this project here, which is bird detection, object detection. And I can turn on the camera and look at this. And turns out that I'm not a bird, which is what I would expect. But then if I try again, this is, anyone know what this is? Yell it out if you know. Kia. It is a Kia, 94%. Now, a Kia looks kind of similar to a kaka. So this is the North Island version. This is the South Island version of the parrot. And so you might want to have a look and see, is it able to detect the difference between these two? Oops. Oops, damn it. We'll find out. Oh, yes it is. 92% on the kaka and 93% on the Kia. So that's a pretty good example or recognition where you might want to use this type of thing. Just to test a little bit more, it's been tested against real birds, but my daughter has a Kia toy, which also makes the noise of the Kia, I think. Maybe it doesn't.
Battery's flat.
So the question is, does it recognize the toy? No. Or maybe it does. No. Not this model. And so that's kind of using the object detection. If I was to turn that into classification as opposed to object detection, I've got another version of the model which is using classification. So if we load up this one over here, there's the bird model loading in with those specific labels. And inside my assets here, I've got the exported ONNX model from Custom Vision. And if I run this one on my local machine, it's going to load up the sample app. This is just in the samples that I've got a link to at the end. And I bring up my bird detection sample. I can test a few images. The fantail that I have on my shirt, it's 100% on that. And this is using classification. So I can then come in and say, yeah, Kia. You notice it on the right-hand side there with the probabilities as I start to show it up. Anyone on that one? Kokako. And the Kia. Yeah, it's got the Kia at that time. So again, useful ways of training. And because I'm in Australia, I probably need an Australian bird as well, the cockatoo. So a great way to kind of come out and identify those different types of models that you might see. And of course, you want to be able to run this on mobile as well. So you can export these models as Core ML or as the TensorFlow mobile and put them into a Xamarin project or a native project that can then run on a mobile device. So I've got an example here which is running on Android. You could also use iOS. There's the TensorFlow mobile example. And if I just deploy this is out on this particular phone. And for some reason, it keeps connecting to this laptop over Wi-Fi instead of the connected one that I've got. So I'll try and reconnect it on here. So I can show it to you. There we go. And there it is there. And here's the same thing running offline on a mobile device. So then I can click on my identifier, it loads the camera, and then I can point at the, cockatoo. I think that it should recognize it. Yeah, hello cockatoo. Try something else. Anyone know what that one is? That is a moorpork. So what I've kind of shown there is, we've gone full circle. We've taken a model that's been trained either as image classification or object detection. We've shown how you can run those in the cloud through an API. We've shown how we can export the models and run them IoT Edge on a mobile device, IoT Edge on a Raspberry Pi or some other kind of small IoT managed device. We've shown an upcoming version of Windows, how we could run that inside of inside of ONNX, and we've shown how you could do that on mobile devices using Android or Core ML. So I know kind of stuck for time a little bit here, but there's a lot of content to go through. But really the message is there's more and more apps, scenarios that are coming out where we want to infuse AI. Computer vision seems to be one of the top scenarios for it, but there's a lot of others around audio detection, language detection, translation, visual search. And then we need a way to simplify, because there's so many frameworks and so many different models out for building these things. You want to be able to export them and use them in a consistent kind of way. And that's what we're trying to do with Windows ML. It's what we're doing with TensorFlow and Core ML as well. And the resources for the talk, we covered a lot. There's quite a lot of code. It's all available up on this link. And this is also shared with the repositories from Azadeh and Dave Barella's talk earlier in the conference, where they showed some examples and they showed some more pieces around the cognitive surge. And with the moments that I've got, I just thought one more scenario that I'd demonstrate just before we close. I actually I was working with a company based out in India that wanted to generate highlights automatically from video, because they had a scenario where they had lots of people sitting in a room automatically tagging videos. So I wanted to see whether I could do that using this type of classifier approach. And I was able to use Python and Python Notebook to actually go away and do that. And what this has done here is this is a classifier that's trained, again, using the bird model that I've got, the kakapo, exported the TensorFlow Lite version of that, and then loading that up inside of Python on the local machine, and then exporting the video down 1 frame per second, and then going through the video and looking for when you detect certain things in it. So the scenario was around sports, wanting to identify when cricket, when wickets happened, or when somebody was highlight feature was there, or reading the scoreboard, those type of things. And you'll notice down here, I found a video on YouTube of a kakapo, and then I've gone through and identified when the kakapo actually turns up in the video. So you can go through, and these are all time slice links to times when the kakapo's in it, as opposed to somebody talking about the kakapo. And you'll see a link there, 31 seconds in. If I go to that particular video, there's 31 seconds in, and there's the kakapo appearing as it walks up towards the camera. So these kind of scenarios of identifying the object, seeing it come into the frame, and then having AI to perform those tasks that would otherwise be manual process for somebody to watch that and say, at what point did that happen? So that was just one closing example that I wanted to share with you. So I know we covered a lot, and I apologize for where the demos did fail, but I think we had a pretty good run. So thank you for that, and we'll be clearing up and then able to talk in the break as well. So thanks a lot.